Welcome to part 3 of our study on rational functions. In this video, we will learn how to find the horizontal asymptotes of our rational function, as well as describe them in terms of end behavior. Now, end behavior is something that we have already studied with polynomial functions, and we've seen end behavior only go towards positive infinity or negative infinity, depending on the degree and the sign of the lead coefficient, whether it was positive or negative. When we have rational functions, our end behavior can also go to infinity or negative infinity as well. However, we also can have something called a horizontal asymptote, which means that our end behavior, instead of going towards positive or negative infinity and not really being bounded at all, it might be bounded by a horizontal line, and that line is called a horizontal asymptote. In this picture right here, this is an example of a rational function that has a vertical asymptote at x equals 2. We discussed those in the previous video. And it has a horizontal asymptote at y equals 1. We can clearly see that the end behavior of this rational function is not infinity or negative infinity. Remember, end behavior is how our graph behaves at its ends, all the way to the right or all the way to the left. And the way that we describe all the way to the right is as x getting larger and larger as x approaches positive infinity. What is our graph doing as x approaches positive infinity? Our graph is approaching 1, y equals 1, this horizontal asymptote. Same thing to the left. We describe our left end behavior, how our graph behaves as x gets smaller and smaller, all the way towards negative infinity. And in this case, our function, our rational function here, its graph is also approaching the horizontal asymptote of y equals 1, just from below it. So our end behaviors here are not positive or negative infinity, rather our end behavior is a number. And when we have an end behavior being a number, that just means it's a horizontal asymptote. So we do have a few rules for horizontal asymptotes, and I recommend that you write those down. We'll make this real small, and here are the rules. So in order to find the horizontal asymptote, we actually find both the degree of the numerator and the degree of the denominator, because again, a rational function is one that has two polynomials, one up top and one down below. We call the degree of the numerator n, and we call the degree of the denominator m, as shown here in f of x. So n is the degree of our numerator, while m is the degree of our denominator. We also see that a and b are the lead coefficients of both the numerator and the denominator, respectively. So we have three scenarios here. Either n is less than m, equal to m, or greater than m. So if n is less than m, meaning the degree up top is less than the degree down below, then our horizontal asymptote is just the x-axis, which is the line y equals 0. If the two degrees are equal, then our horizontal asymptote is the ratio of those lead coefficients. It's a over b. Remember, a is the lead coefficient of the numerator, while b is the lead coefficient of the denominator. That's actually the case up here. Their ratio must have been 1. And then in the final situation, if the degree of the numerator is larger than the degree of the denominator, then we actually have no horizontal asymptote. There's actually something called a slant or oblique asymptote, which we are not going to get into in this class, but if you're curious, your book does delve into that topic. No horizontal asymptote means that our function's end behavior approaches positive and or negative infinity on both ends. It's not bounded by any horizontal line. So make sure you have this written down in your notes, and we will go into some examples next. Here we want to find the horizontal asymptotes of these three functions. I did keep the rules for finding the horizontal asymptotes down here so we could reference them easily. So what we want to do is, in number 1, find the n and m values. So n, again, is the degree of the numerator. And so we have 5x to the first. That means the degree of our numerator, n, is 1. And then the degree of our denominator is 2. So m is 2. So we actually have that n is less than m. We have the first scenario here. The horizontal asymptote is actually the x-axis, which is the line y equals 0. So our horizontal asymptote is the line y equals 0. Let's take a look on the graph and make sure that that is the case. This is a really fun looking graph. I am enjoying it quite a bit. So we can clearly see in here that while it's very strange in the middle, as we look to our end, so let's explore all the way to the right, as x approaches positive infinity, we can clearly see that our graph is approaching the x-axis. We have the right end behavior of 0. That is the horizontal asymptote. It's the x-axis, the line y equals 0. And same thing all the way to the left. Our rational function approaches the x-axis, aka the line y equals 0, as x gets smaller and smaller and goes towards negative infinity. And even though it's approaching it from the opposite side as from the right, that's okay. We're still approaching the horizontal asymptote of y equals 0. Let's take a look at number 2. Again, to find the horizontal asymptotes, we have to identify n and m, the degree of the numerator and denominator. So the degree of the numerator, n, is 2, while the degree of the denominator, m, is 1. So in this scenario, we have that n is greater than m. So we look here at our rules, and in that case, there's actually no horizontal asymptote. That means that our graph is not bounded by a horizontal line. Let's take a look and make sure that that is the case. So this is also a pretty cool graph. If we take a look all the way at the ends, because that's what we're really looking for, if we look all the way to the right, we can clearly see that our function is approaching positive infinity. So it's not bounded by a horizontal line. It actually does have what's called a slant or oblique asymptote, which is like a diagonal line that it's bounded by. And if you're interested in finding that, you can just do long division, and whatever you end up getting is actually the slant asymptote, which is pretty cool. Now, if we look all the way to the left, we can see that our graph is also not bounded by a horizontal line, and instead it's bounded by a slanted line instead. So we actually do not have any horizontal asymptotes with this graph. Lastly, in problem number 3, we again want to find the values of n and m. And our n value, the degree of the numerator, is 3, while our m value is also 3. Be careful because this polynomial in our denominator is not written in standard form. It's just written in out of order, technically. So this is actually our leading term, negative 2x cubed. It contains our degree and our lead coefficient, the b value. Now, we do care about those lead coefficients because in this scenario, n and m are equal. Therefore, the horizontal asymptote is the horizontal line y equals a over b. So our a value here is actually 6 because it's the leading coefficient in the numerator, and our b value is actually negative 2, our leading coefficient in the denominator. Therefore, our horizontal asymptote is the line y equals 6 over negative 2, which simplified is the line y equals negative 3. I do realize I forgot to write number 2, the answer. The horizontal asymptote is actually none. Let's take a look at our graph once more and make sure that we do in fact have a horizontal asymptote of y equals negative 3. Once again, we have a pretty interesting graph. The moral of the story here is that rational functions are way cooler than polynomial functions just because they're more interesting. So if we take a look here, we're pretty interesting in the middle, and then we do level out on the ends and approach y equals negative 3. Now, the neat thing about Desmos is that you can sort of trace and see what the coordinate points are. As x gets very, very big, note I have points like, 23.45, and then the y value is negative 2.998, meaning it's approaching negative 3 as we get very, very large. So if you went way out to the right, I'm only to like 50, it says negative 2.999, and then it ends up just rounding to negative 3. Technically, we never approach negative 3, or we never hit negative 3, we only approach it. But once we get so close to negative 3, the program will just round it. If we look all the way to the left, our left end behavior should also be approaching the horizontal asymptote of y equals negative 3, and we can clearly see that that is also the case here. So horizontal asymptotes are just a horizontal line that our graph approaches as x gets very large and approaches positive infinity, and as x gets very small and approaches negative infinity. If you do not have a horizontal asymptote with your graph, that means that our graph approaches positive and or negative infinity on the ends and is not bounded by any horizontal line.